What are the chances that two distant stars would suddenly erupt into brilliance visible to the naked eye, while almost simultaneously, powerful earthquakes ripped through Venezuela, and at the same time, a wandering interstellar traveler got slammed by a burst of solar fury? If this were the plot of a film, any Hollywood studio would toss it aside as too far-fetched to sell. Yet, this isn't fiction. It's the chain of real events that unfolded in one of the most extraordinary 72-hour windows in recent memory. What just happened borders on theatrical, a cosmic performance so synchronized that even skeptics are whispering about something bigger than coincidence. Tonight, we're going to break down each event carefully, dive into the science, and question whether randomness truly explains it all, or if something far stranger is at play. Stick around until the end, because what we uncover about September 2025 may rattle assumptions we've held about both Earth and the universe around it. It began with a sequence that feels scripted by the cosmos. Two novas ignited in our skies, twin earthquakes rocked Venezuela, and an interstellar object named 3I Iratus was caught in the path of a violent coronal mass ejection, all unfolding within just 3 days. If this cosmic cluster leaves you feeling like the universe is hinting at something, you're not the only one. Let's retrace what went down. On September 23rd, astronomers recorded the sudden outburst of V1935 Centauri in the southern constellation Centaurus, glowing at a brightness where anyone could step outside and see it without a telescope at magnitude 5.8. Barely days later, another stellar eruption declared itself, V7994, Sagittarii blazing out in Sagittarius, its light strong enough to shimmer into naked eye range at magnitude 6.2. For once, the ordinary night sky transformed into a theatre of cosmic fireworks for anyone who cared to look up. But while the heavens were setting themselves alight, Earth was busy shaking below. On September 24th at 22:21 UTC, Venezuela was struck by a magnitude 6.2 earthquake near Men Grande, in Zulia State, originating from a depth of 7.8 kilometers. The tremors rolled outward, jarring cities and towns across Venezuela and reaching into Colombia. Nature, however, had no intention of stopping there. Hours later, before dawn on September 25th, a second quake of magnitude 6.3 ripped through the same region from 14 kilometers beneath the ground. Back-to-back quakes mirroring the twin novas overhead left geologists and ordinary citizens alike stunned by the timing. As if that weren't enough, above Earth's trembling crust, space itself was staging another dramatic act. The NOAA Space Weather Prediction Center had been tracking streams of coronal mass ejections. Massive clouds of plasma ejected from the sun at over 1 million miles per hour. These roiling solar storms appeared to be intersecting with something unique 3I Atlas, only the third confirmed interstellar traveler to enter our solar system. Here's where the story edges into cinematic synchronicity. Between September 23rd and 25th, novas brightened the skies, the quakes convulsed Venezuela, and solar weather surged. Meanwhile, Atlas, a cosmic drifter discovered just 2 months earlier by the Atlas survey system, was threading its way through the inner solar system during one of the most active phases of the sun's current cycle. Events separated by light years, continents, and astronomical scales had all clustered over the same window in time, leaving scientists with a puzzle bigger than the sum of its parts. Centauri and Sagittarius erupted from constellations that sit far to the south, their light traveling thousands of years only to arrive in our skies during this very week. The Venezuelan tremors struck a tectonically convoluted region where the Caribbean and South American plates push and grind endlessly. The solar ejections burst across the heliosphere, a space so massive it rivals the orbit of Jupiter, and Atlas meanwhile weaved its path through the ecliptic, placing itself in the arena where planets and storms collide. Now, mainstream science cautions against drawing causality out of coincidence. The US Geological Survey maintains that space weather and seismic activity have no measurable connection. Solar physicists will tell you that coronal outbursts are ordinary behavior during solar maxima. Stellar astronomers, too, will assure that novas are standard, if somewhat unpredictable, evolutions of binary stars. And yet, what makes this moment unique is Atlas itself, a voyager not from our solar system but from distant star fields, and this is the first time humanity witnesses such an object directly weathering the blasts of solar fury. Past encounters prove this isn't trivial. In 2007, the European Space Agency's stereo satellites caught a CME violently severing the iron tail of Comet Encke. If the Sun can whip apart comets that have circled it for eons, what could it do to an object birthed light years away, one shaped under completely different suns? That's the kind of question keeping astronomers glued to their monitors. The script only grows more intense from here. Atlas is set to skim by Mars on October 3rd, coming within 28 million kilometers of the red planet. NASA's Mars Reconnaissance Orbiter and ESA's ExoMars mission are already lining up opportunistic observations, hoping for details of this alien interloper at a clarity we've never achieved before. Then, on October 29th, Atlas reaches perihelion, drawing nearest to our Sun at 1.36 AU. It won't swing inside Earth's orbital path, but it will be close enough for telescopes around the globe to watch it in real time, with exquisite detail. The climax arrives on December 19th, when Atlas brushes by Earth's vicinity at 1.8 AU, closer than Mars is at its farthest distance. This means months of monitoring, from the world's biggest observatories to backyard stargazers. And this is happening just as Earth steps into its season of intensified space weather. During the equinox, a magnetic geometry known as the Russell-McFerrin effect makes Earth more vulnerable to geomagnetic storms. Historically, September through November unleash some of the brightest auroras and strongest technological disruptions. With Atlas drifting across our skies during this exact window, the timing couldn't be sharper. The promise here is clarity, but also wonder. You will hear both the hard science and the daring what-if questions, each separated clearly along the way. Some patterns may prove purely coincidental. Others may suggest larger connections. But even scientists will admit that sometimes all we can say is, we're watching closely and we don't yet know. And that uncertainty is exactly what makes this unfolding story so magnetic. So pause and consider. If solar storms have snapped the fragile tails of comets forged in our own system, what could happen when that same power lashes against a structure that has survived a journey spanning millions of years from another star? That's the mystery lying before us as Atlas charges deeper into the Sun's firing line. Up next, we'll explore the twin novas, two sudden bursts of stellar brilliance lighting up the southern skies, just as Earth's crust began to shudder. What John Setch spotted that morning would quickly send ripples through the entire astronomical community, capturing the attention of orbiting gamma-ray detectors and X-ray observatories scattered across the solar system. The star V1935 Centauri didn't announce its arrival with any dramatic flourish, but instead by releasing a flood of photons. At first, Setch's detection looked simple, a dim patch of sky suddenly bright enough to register at magnitude 5.8, just visible to sharp-eyed skywatchers in areas dark enough to escape city lights. Yet this was no ordinary increase in brightness. The moment his report reached the Central Bureau for Astronomical Telegrams, a cascade of space-based instruments started pinging with unusual signals. NASA's Fermi Gamma Ray Space Telescope picked up a burst of high-energy radiation flaring from that same region of sky. Within hours, the Swift Observatory, typically tuned to catch cosmic explosions, pivoted its powerful X-ray telescope and began recording streams of hard X-rays emerging from Centaurus. What these instruments saw wasn't just a pretty celestial flash. It was evidence of nature pushing physics to its extreme edge. Electrons and protons were being catapulted to nearly light speed. Magnetic fields writhed and twisted like tangled wires. Temperatures skyrocketed to the kind of heat rarely seen outside the hearts of stars. For scientists, this was a front-row look at violent processes that can reshape stellar systems in an instant. But V1935 Centauri wasn't the only star-stealing headlines. Mere days later, the cosmos delivered yet another spectacle. The star V7994 Sagittarii erupted in the neighboring constellation Sagittarius, flaring up to a brightness of magnitude 6.2 when first spotted. Two novas, both caught by the same observer, both bright enough for binoculars or small telescopes, flashing to life in the same extraordinary week. Ordinary novas aren't exactly rare. Astronomers record roughly a dozen across our Milky Way each year. But for two to grow bright enough for amateur astronomers to easily track within a matter of days, that's exceptionally rare. You'd have to rewind to 2023 for the last time sky watchers saw such a double act in real time, and before that, years would pass without anything comparable. What makes novas so fascinating isn't just the light, they're the exclamation marks in the story of stellar survival. Novas are powered by dead stars that refuse to stay quiet. At the heart of each eruption lies a white dwarf, the compact burning core of a long-dead sun-like star, compressed to something Earth-size but with a mass rivaling our Sun's. These stellar remnants often orbit a living companion, patiently pulling a stream of hydrogen gas off their partner over long stretches of time. The stolen material wraps around the dwarf like a suffocating blanket, pressurized more with each passing day. Eventually, conditions hit a critical threshold. The trapped hydrogen detonates in an uncontrolled burst of thermonuclear fusion, a cosmic bomb that can suddenly make the star flares thousands of times brighter. The white dwarf itself survives, stripping away its outer layer in the explosion, only to begin the slow, patient theft process all over again. Some white dwarfs have predictable cycles, sparking new novae every few decades. Others may lay dormant for centuries or even millennia before erupting. What stood out about V1935 Centauri, however, was the ferocity of its outburst. The gamma-ray and X-ray detections confirmed this wasn't a quiet firework but a storm of violent physics. Its expanding shockwave hurled material outward at thousands of kilometers per second. Colliding matter and twisted fields accelerated particles to extreme energies, producing high-energy radiation eerily similar to what we see in supernova remnants or the blazing cores of distant galaxies. For astronomers, this nova was behaving like a miniature particle accelerator parked in our sky. For those watching from Earth, geography decided who had front-row seats. Both V1935 Centauri and V7994 Sagittari sit deep in southern skies. Observers south of the equator had pristine views as the novas climbed high into their night. Those living in mid-northern latitudes had to wait for the stars to skim low along the southern horizon, visible only under exceptionally dark conditions. The discoveries themselves revealed the highly cooperative orchestration of modern astronomy. Seccha's first reports travelled quickly through the International Astronomical Union's Central Bureau, sparking immediate follow-ups across the globe. Circular 5611 confirmed V1935 Centauri, while Circular 5612 announced V7994 Sagittari soon after. Within days, professional observatories were collecting precise brightness measurements and spectral data, detecting hydrogen, helium, and heavier elements expanding into space. Yet it wasn't only professionals logging data. Amateur astronomers, especially those in networks like the American Association of Variable Star Observers, became an indispensable part of the campaign. With backyard telescopes, they contributed nightly observations, tracking the evolving brightness curves. These light curves tell the story: sudden peaks, plateaus, dips, sometimes even unexpected re-brightenings. They reveal the hidden physical processes inside these explosions, moments that big telescopes might miss during gaps in their observing schedules. To newcomers, the naming system can be bewildering. V1935 Centauri simply means the 1935th recognized variable star in the constellation Centaurus. V7994 Sagittari follows the same rule, 7994th in Sagittarius. The numbers don't follow discovery sequence, so it can look confusing when new stars are catalogued or updated, but once a nova's designation is recorded, it permanently becomes part of the astronomical directory. Like most novas, these two will fade over weeks and months, their brilliance fading back into sky maps, where they'll once again be indistinguishable from millions of others. But their fade-out may not be entirely smooth. Some novas surprise astronomers with late twists, darkening temporarily as dust forms in their ejector shells, or brightening in unexpected aftershocks. Light curves sometimes split into multiple peaks, with effects driven by interactions scientists don't fully understand. Now comes the question sparking debate outside the observer's field of view. Was it pure chance that these two novas exploded just days apart during the same week Earth endured twin earthquakes and powerful solar storms battered space weather systems. Professional astronomers emphasize caution. Stars thousands of light years away, locked in binary systems, unleash their fury without any connection to terrestrial activities. The energy crossing interstellar distance dwindles into faint starlight, powerful to study, but utterly harmless on Earth. From the scientific point of view, these events are unrelated. And yet, timing nags at the imagination. Twin novas shining as twin earthquakes strike, all while an interstellar object threads its way through solar tempests. It feels layered with symbolism, as though the universe staged a performance we were never meant to miss. Maybe that's simply our human tendency to weave patterns. But maybe once in a while the randomness of cosmic rhythms aligns into something so compelling it borders on poetry. And while the night sky was dazzling watchers with explosions of starlight far away from observatories deep in Venezuela, the Earth itself was preparing an eruption of its own, proving that cosmic fireworks weren't the only explosions making headlines that week. A magnitude 6.3 quake might only sound like a small step up from a 6.2 comma, but in terms of energy release, it's nearly double. When you add the Venezuelan twin shocks together, the combined force looked like a single quake in the 6.4 to 6.5 range, an impressive amount of energy by any global benchmark. In fact, these September 24th and 25th ruptures stand as the most powerful seismic activity recorded in that part of South America since the devastating 7.8 earthquake in Kamchatka on September 18th, putting Venezuela's back-to-back events squarely among late September's most significant global seismic stories. The Earth, however, wasn't content to stop there. Hours after the twin main shocks, an aftershock of magnitude 5.8 rolled through the same fault zone. For seismologists, this fit the classic Omori pattern of aftershock decay, powerful quakes triggering smaller trailing rattles. While 5.8 might sound modest compared to its predecessors, it was anything but comforting for people already shaken by 2 nights of violent ground motion. Strong enough to rattle buildings, break fragile structures, and spike public fear, it added another chapter to a saga of stress that the region won't soon forget. To understand why this region is so earthquake-prone, you have to zoom in on its tectonic architecture. Northwestern Venezuela lies within the Maracaibo Basin, one of the most geologically complicated collision points on Earth. Here, the Caribbean plate collides and scrapes against the South American plate, creating a fractured landscape stitched with fault systems like the Bocono and the Ocoancon-Santa Marta structures. Every push and grind between plates builds stress over decades or even centuries, until a sudden slip sets that stored energy free. That violent redistribution of force is what locals felt as the ground convulsed beneath their feet. The difference in quake depths also helps explain the intensity. The September 24th tremor came from just 7.8 kilometers below the surface, while its September 25th counterpart struck deeper at 14 kilometers. Shallow quakes pack a harsher punch, because the seismic waves travel a shorter path before hitting the surface, arriving with far more destructive power. That explains why the first jolt was widely reported across Venezuela and Colombia, shaking buildings, toppling furniture, and sending millions surging into the streets. If you look at official reports, you'll notice the magnitudes vary slightly between institutions. The US Geological Survey logged the first quake at 6.2, while European and Mediterranean agencies listed values ranging between 6.1 and 6.3. That discrepancy isn't contradiction. It's the nature of earthquake science. Measuring quakes involves multiple magnitude scales: body waves, surface waves, moment magnitudes. As more seismic stations feed in real-time data, initial estimates get refined. But regardless of whether one authority called it 6.1 and another 6.3, the human experience of these tremors remain the same: intense, frightening, and widespread. The real story, of course, is not only in numbers but in people's lives. The thousands were evacuated across Zulia State, especially from high-rise buildings that swayed for what felt like endless minutes. Emergency responders fanned out to inspect hospitals, power plants, and bridges. Rapid assessments showed that much of the critical infrastructure remained intact, a testament perhaps to luck, timing, and ongoing improvements in building codes. Still, engineers warned of hidden stresses inside concrete, fractures in structures that might not reveal themselves for months or years to come. The history of this region makes the twin quakes unsurprising, if no less unsettling. The tectonic seams near Lake Maracaibo and along the Caribbean-South American boundary host regular ruptures, though not often this large. What adds intrigue is the possibility of stress transfer. When one fault slips, it changes the pressure along surrounding faults, sometimes triggering additional activity in the days or weeks that follow. That's why seismologists cautioned against ruling out more large events. Scientifically, no one can predict with certainty whether another major quake is imminent. Aftershocks are expected and can continue for weeks, but the leap to forecasting something bigger remains beyond current science. Despite decades of research, earthquake prediction is still one of geology's most elusive frontiers. While scientists dissected the mechanics, international monitoring networks captured every aftershock to build an evolving map of the stress redistribution. The Global Centroid Moment Tensor Project ran fault plane analyses, teasing out which segments shifted, how the crust contorted, and what stress now lingers unspent. For the people of Venezuela, however, data offered little comfort compared to lived reality. Back-to-back nights of terror and the humbling reminder that their homeland sits on restless ground. Surprisingly, the damage, while real, wasn't catastrophic. Fewer collapsed buildings than expected, fewer fatalities than feared. Analysts pointed out that the quakes struck at times when many were home instead of working in vulnerable urban structures. Combine that timing with stronger construction standards enforced in recent decades, and the story could have been far worse. Still, the psychological scars left behind remind the population that preparedness remains as vital as engineering. What makes this chapter especially captivating is its place in the bigger puzzle of late September 2025. Two novas flared in the southern skies. Solar activity surged. An interstellar object crossed Earth's neighborhood, and Venezuela endured twin quakes. As scientists emphasize, geology has no proven connection to space weather or stellar fireworks. The US Geological Survey maintains there is no evidence linking solar storms to seismic activity. Skeptics are quick to dismiss cosmic coincidences as just that, coincidences. Still, the timing tugs at the imagination. Pattern-seeking minds can't help but notice how the Earth groaned at the same moment the heavens blazed. For scientists, the most honest answer isn't poetic, it's careful. Document the timeline. Study each event on its own terms, remain open to new connections without leaping to cause and effect. But for the rest of us, the clustering of violent earthquakes under a sky alive with novas and solar storms almost feels like choreography, a grim yet beautiful reminder that Earth and sky are never truly separate stages in the cosmic theatre. And while Venezuela processed its shaking ground, just 93 million miles above, our sun was staging eruptions of its own, coronal mass ejections that would cross paths with something no human generation had ever witnessed before, an interstellar traveler caught in the line of fire. When the sun's tangled magnetic fields snap and reconnect, the energy released is staggering, on the order of billions of hydrogen bombs detonating at once. That unleashed power hurls plasma outward at speeds ranging from 250 to nearly 3,000 kilometers per second. At those velocities, a blast of solar material can cross the 150 million kilometers between the Sun and Earth in as little as 1 to 4 days. To predict these storms, NASA's Space Weather Prediction Center relies on an advanced computer system known as the WSAN-NIL model. This simulation maps the entire solar wind environment, using data on speed, particle density, and magnetic polarity to forecast exactly how coronal mass ejections, or CMEs, travel through the solar system and which spacecraft or planets might lie in their crosshairs. In late September 2025, those NEL forecasts showed a crowded stage. Multiple CMEs were surging through the inner solar system at the exact same time Earth was being shaken by earthquakes, and the skies were flashing with novas. But this sequence carried a historic first. For as long as humans have recorded space weather, this was the very first time a solar storm was on track to collide with something not from our system at all. An interstellar visitor called 3I Atlas. Discovered just 2 months earlier by the Atlas All-Sky Survey, Atlas was making its way through the inner heliosphere against a backdrop of maximum solar activity. Its path was unusual, a highly tilted retrograde orbit cutting across the ecliptic plane, the same broad disk where Earth orbits and where most solar storms concentrate. Essentially, this object stumbled right into the firing line of our star during one of its angriest phases. To understand how significant that is, we can look back at what happens to ordinary comets when they cross paths with CMEs. The evidence isn't theory, it's been caught on camera. In 2007, Europe's stereo satellites filmed a solar storm ripping the iron tail clean off Comet Encke. For several hours, the comet's magnetic umbilical cord to the Sun was severed, drifting away into space before a new tail began to form. The reason this happens lies in the two kinds of tails that comets carry. Dust tails, made of tiny grains pushed by sunlight, curve gently away in elegant arcs. Iron tails, however, are formed by charged gas interacting with the Sun's magnetic field, and these point straight outward. When a CME slams into that delicate structure, it can literally disconnect it, scattering the tail and forcing the comet to start rebuilding from scratch. So what does this mean for 3I Atlas? The suggestion that it was clipped by one of these solar storms comes not from photographs but from computer modeling. ML simulations showed that the eruption paths overlapped with the comet's exact position during the last week of September, but as with all models, there's uncertainty. They're excellent at broad predictions yet less precise about the finer details of timing and geometry. What we may be witnessing is an inference rather than a verified observation. If the interaction did occur, here's what scientists and amateurs alike were watching for. The coma, the glowing haze of gas around the nucleus, might flare in brightness as additional solar energy ionized more material. Tail structures could twist, fragment, or even briefly vanish as magnetic turbulence snapped established field lines. Spectrographs could record sudden chemical signatures as molecules like carbon monoxide and cyanogen were blasted loose from the object's frozen shell. Amateur astronomers play a critical role in this detective work. Using coordinated observation networks and global forums, countless backyard telescopes provide images night after night. When stitched together, those frame-by-frame visuals reveal subtle changes in tail angles, brightness, and morphology that sometimes slip past large telescopes focused on broader projects. In many ways, crowdsourced astronomy makes it possible to track a living, moving phenomenon in real time. What makes this especially thrilling for scientists is not just the beautiful fireworks, it's the opportunity. 3I Atlas isn't bound to our solar system at all. It's the third interstellar object we've ever confirmed after Oumuamua in 2017 and Borisov in 2019. But unlike them, Atlas has wandered directly into the thick of solar activity during an active maximum. This means our star could be directly and measurably shaping material forged around a completely different sun, maybe billions of years ago. It's the first time humanity can watch our sun's magnetized fury interact with a traveler from another stellar system. The geometry makes it even more advantageous for us than previous visits. Oumuamua, for instance, passed quickly at a steep angle, barely lingering near the ecliptic where solar fireworks are most intense. Atlas, by contrast, is crawling across that key plane, moving where solar storms most often funnel their energy. Combined with solar cycle 25 revving at full strength, with sunspot counts surging, flares erupting more often, and CMEs flying regularly, Atlas is encountering a stormy sun few other interstellar objects will ever endure. Confirming any CME effect requires patient science. Analysts are combing through sequences of brightness shifts, spectral fingerprints, and evolving tail geometries captured over hours and days. Professional observatories and networks of amateurs alike are comparing notes. While initial reports in late September were still being analyzed, the possibility remained electrifying. Our sun may have just altered the appearance and chemistry of matter that has been in deep space for millions of years. The implications are galactic. If we capture how solar storms sculpt this alien object, we can apply the same physics to countless other stars. Every sun likely hurls out CMEs into space. Every wandering comet-like object that drifts through another system will experience those blows. Atlas may carry scars not just from its flyby of Earth's sun, but from previous encounters with entirely different stars during its eons-long voyage. In other words, it may be a fossil record of interstellar weather written across its icy surface. That late September week had already dropped multiple anomalies into our lap. Twin novas, twin earthquakes, a hyperactive sun, and now an interstellar object caught in the crossfire. Coincidence or convergence, pure random timing, or a deeper pattern emerging? Science keeps us cautious, reminding us not to force connections. Yet it's hard to ignore the poetry for the first time. Humanity may be watching its star physically reshape a piece of matter born beneath a different one. And as 3i Atlas pressed onward toward its early October flyby of Mars, scientists braced for answers, silent clues etched into its hazy coma and fragile tail, evidence of how a foreign traveler responds to the breath of our volatile sun. And coincidences, while fascinating, aren't always comfortable. Our minds are wired to notice connections, even when none exist. It's the survival system that once kept our ancestors alive. The rustle in tall grass that might signal a lurking predator, the cloud pattern that could mean oncoming rain, the subtle shift in someone's expression that hints at threat or opportunity. This mental architecture helps us navigate uncertainty, but it also makes us prone to overread randomness, turning clusters of unrelated events into patterns with imagined meaning. The scientific consensus is firm. No evidence links solar storms to earthquakes. The US Geological Survey has repeated this for years. Decades of attempted correlation studies reveal no statistically reliable connection between seismic activity and solar outbursts. Likewise, seismologists remind us that earthquake prediction doesn't exist. Despite decades of monitoring stress patterns, foreshocks, electromagnetic surveys, and computational models, there is still no way to forecast an earthquake ahead of time, let alone tie it to activity on the sun. Astronomers give similarly grounded explanations for novas. They aren't cosmic anomalies or omens, but textbook consequences of binary star systems in which white dwarfs siphon gas from their companions until thermonuclear runaway turns a quiet object into a brief beacon visible across space. The explosions may be spectacular, but they're predictable within stellar evolution. V1935, Centauri V7994, Sagittari may sit in headlines now, but scientifically, they are regular episodes of long-running astrophysical cycles. Solar physicists take the same stance on coronal mass ejections. Far from being mysterious harbingers, they are understood as the result of snarled magnetic fields in the sun's corona snapping under pressure. And during solar maximum, precisely the phase we currently occupy, they are common. The interaction of CMEs with comets is also no mystery. It is plasma physics in plain sight, directly observed and documented in multiple peer-reviewed studies. But here's the nuance. Acknowledging the straightforward scientific interpretations doesn't mean brushing aside the remarkable timing of it all. When novas, quakes, and an interstellar object all converge in the same week as a sun ravaged by activity, the coincidence feels bigger than the sum of its parts. Statistically mundane phenomena can still align in ways that strike the human imagination as synchronous or almost poetic. The challenge is to hold two truths at once: skepticism guided by evidence and wonder inspired by patterns. That dual lens is how we'll continue. Our approach rests first on solid ground, the measurements, magnitudes, coordinates, spectra, seismic readouts, what instruments and satellites recorded. On top of that base, we place the verified science that explains why those readings occur, rooted in stellar physics, seismology, and plasma models. And above that, we allow ourselves a cautious step into speculation. Clear boundaries will mark which ideas live in verified fact, and which belong to the realm of what-ifs possible but not proven connections between cosmic events and earthly changes, hypothetical influences of distant stellar events on local system dynamics, or potential feedback loops not yet discovered. Language matters, so let's pause and decode a few basic terms before we continue. A nova brightens a star system thousands of times over, caused by runaway fusion on the surface of a white dwarf. A supernova is entirely different, catastrophic and final, obliterating the star. A coronal mass ejection is a billion-ton plasma cloud hurled into space at immense speeds, carrying magnetized gas across the solar system. Perihelion is the point in an orbit where an object sweeps closest to the sun. One astronomical unit, or AU, equals Earth's average distance from the sun, 93 million miles, or about 150 million kilometers. And comet tails break into two types: dust tails, bent elegantly by sunlight, and ion tails, long straight spines that trace magnetic field lines across millions of kilometers of space. When CMEs disrupt those fields, ion tails can quite literally snap and drift away before reforming. In the weeks ahead, we'll separate layers step by step, observed events, tested science, and speculative frontiers. We'll revisit the physics of novas, the mechanics of earthquakes, and the plasma theatre of CMEs. We'll track Atlas through its Mars flyby on October 3rd, then its closest brush with the Sun on October 29th. Along the way, we'll weigh what mainstream science says against ideas sitting further out on the speculative edge, and we'll label each clearly so you know where fact ends and possibility begins. Some of the additional context comes from seasonal space weather. Around the autumn equinox, Earth's tilted magnetic geometry interacts more strongly with solar storms, an effect called the Russell-McPherson coupling. This heightens geomagnetic impacts in September and October, even without any correlation to earthquakes or novas. In that sense, Earth was primed for vibrant auroras and strong disturbances, independent of what else was happening. But 3I Atlas is what keeps astronomers on edge in this moment. It is only the third confirmed interstellar visitor humanity has ever detected. Unlike Oumuamua, which zipped through too fast for in-depth analysis, or Borisov, which remained relatively far from Earth's orbit, Atlas is threading the very plane where so much of our solar system's drama unfolds. Solar eruptions, planetary alignments, spacecraft, all live here. Its proximity, combined with solar cycle 25 running hot, makes this the first interstellar traveler humanity will be able to watch as it tangles directly with solar weather, not for minutes, but for months. And there's more at stake than curiosity. On October 3rd, as Atlas brushes near Mars, orbiters around the Red Planet, including NASA's Mars Reconnaissance Orbiter and ESA's Trace Gas Orbiter, will seize a once-in-history chance to image the object's nucleus and coma. The detail they could capture would eclipse anything we've ever known about such visitors. By late October and December, telescopes across Earth will continue following it, recording changes to its brightness, chemistry, and tail morphology. Meanwhile, Venezuela's aftershocks will rumble on, just as seismologists expect after strong ruptures. Monitoring networks will keep scanning regional stresses even though no one can forecast when or if another large quake might strike. The region remains active by geological definition, its future quakes inevitable though their timing unknowable. So here is the promise as we continue. We will balance realism with curiosity. We will give mainstream science its center stage because that is where evidence stands strongest, but we'll also respect hypothesis, placing speculative ideas in their own frame rather than erasing them. And we'll acknowledge something that transcends science, the human urge to find patterns, to make meaning out of chaos, to find poetry in coincidence. What makes this late September convergence so extraordinary isn't just the events themselves, it's us. For the first time in history, people alive today have the instruments, satellites, and real-time global networks to track novas exploding light years away, interstellar wanderers passing nearby, space weather crackling across the solar system, and earthquakes shaking our crust. Generations before ours might have gazed at a sudden nova or staggered during a quake, but they would never have connected those moments into a shared timeline. We, however, can. And so we keep asking, what exactly drives a nova? How does a star explode without tearing itself apart entirely? The answer leads us back into the heart of stellar physics, where even the most familiar cosmic objects reveal forces that push the boundaries of human comprehension. Part 6. The Anatomy of a Nova. Imagine a star collapsed into an object no bigger than Earth, yet containing the entire mass of our Sun. This is a white dwarf, a cosmic ember left behind after a sun-like star runs out of fuel, blows away its outer layers, and shrinks into a sphere of degenerate matter. Its surface gravity is so crushing that a thimble of material would outweigh a mountain back on Earth, its density soaring to nearly 1,000,000 times that of water. Surface heat lingers around 50,000 degrees Fahrenheit, making it a stellar corpse that still burns with remnant fury. Now place this dense survivor in orbit with a swollen companion star, often a red giant whose outer atmosphere has ballooned outward with age. The white dwarf, with its fierce gravity, quietly robs its neighbor of hydrogen, siphoning gas across interstellar space in thin spiraling streams. Over time, the stolen atoms accumulate in a blanket across the dwarf's surface. For decades or centuries, the material piles higher, weighed down by crushing gravity. With each passing moment, the temperature and pressure increase, driving the trapped gas toward instability. When the pressure crosses a critical threshold, sudden ignition occurs. At around 100 million degrees Kelvin, nuclear fusion erupts, not the steady, controlled process that keeps living stars burning, but an uncontrolled chain reaction. Within seconds, the white dwarf's accumulated hydrogen explodes in a runaway fusion event. The star system brightens by thousands of times, producing what we recognize as a nova. But here's the key: the white dwarf itself is not destroyed. Only the outer layer of borrowed hydrogen is blasted into space, leaving the dense remnant intact, ready to begin the cycle again. This is what astronomers saw when V 1935 Centauri flared in September, its eruption violent but survivable. That violence drew the eye of space telescopes because it wasn't just pretty starlight for backyard observers, it was particle physics on a grand scale. NASA's Fermi Gamma Ray Telescope recorded bursts of high-energy photons, evidence of matter being accelerated to near-light speeds in the nova's shockwave. Swift, with its X-ray vision, caught signatures of electrons whipped through magnetic fields at ferocious energies, generating radiation across the spectrum. In essence, novas behave like natural particle accelerators, blasting out cosmic rays at energies rivaling the biggest machines humans have ever built. Surrounding the star, a spherical shell of material surged outward at thousands of kilometers per second. As this blast plowed into surrounding interstellar gas, shock fronts formed. These shocks twisted magnetic fields and catapulted protons and electrons into violent speeds, producing energy phenomena similar to what we see in distant galaxy cores. The ejected cloud glowed as chemical elements, hydrogen, helium, and heavier compounds flashed into emission lines that spectrographs could pick apart for clues. And while professional observatories provide in-depth analysis, much of the story is built night after night by amateurs across the globe. Through organizations like the American Association of Variable Star Observers, hundreds of backyard astronomers record light curves, graphs of brightness over time, with nothing more than telescopes or CCD cameras. Their data fills a crucial need, providing continuous monitoring that big observatories with their packed schedules cannot. These light curves reveal the nova's rise, plateau, and decline phases. Sometimes they also show surprises, rebrightenings, dust dips, and other quirks that hint at complex processes we still don't fully understand. In general, a nova rises to visible brightness in days or weeks, lingers at peak for anywhere from a few nights to several months, and then gradually fades across months or years as the debris cools and disperses. Sometimes secondary peaks punctuate the decline, driven by changes in the expanding shell. On rare occasions, dust condenses within the nova's ejecta, briefly dimming the system as tiny grains scatter light. These dust dips can plunge a nova's brightness by several magnitudes before the haze disperses, letting the star shine again. Distance adds another layer of awe. Both VE 1935 Centauri and VE 7994 Sagittari almost certainly lie thousands of light-years away, which means their explosions actually happened long before human civilization built cities, wrote language, or cast our first shadows in firelight. For millennia, their signals traveled silently across space, arriving here just in time to be part of this extraordinary week in 2025. It doesn't take advanced equipment to join this cosmic investigation. Observers with ordinary DSLRs and telephoto lenses can photograph a nova in its bright phase. Binoculars or hobby telescopes let amateurs estimate brightness visually by comparing it to nearby stars. And with CCD cameras, precise magnitude measurements can be logged that rival professional standards. Each observation, from the simplest visual estimate to the most detailed spectrum, contributes another piece to the puzzle. As for names, the designations can appear cryptic. The B in V 1935 Centauri simply marks it as a variable star, the 1935th, discovered in its constellation. Similarly, V 7994 Sagittari is just the 7994th recorded in Sagittarius. These designations replace temporary discovery names, ensuring each nova's place in astronomy's permanent catalogue. The raw physics underscores the extraordinary scale. A typical nova radiates as much energy as the Sun produces in 10,000 years, all unleashed in weeks. Enough to power human civilization for billions of years at today's consumption levels, though still dwarfed by the titanic forces of supernovae, which can outshine galaxies. Some systems repeat this process. Recurrent novas blast every few decades, each eruption stripping and reshaping their stellar shells, slowly approaching the dangerous Chandrasekhar mass limit, at which the white dwarf itself may collapse in a Type Ia supernova. Professional follow-ups are already underway. Hiroshima and NACE telescopes are tracking brightness and spectra. Hubble may capture high-resolution imagery of the expanding shells. Radio arrays are listening for synchrotron signals from accelerated particles, filling in the multi-wavelength puzzle. And spectroscopy continues to confirm the obvious. These are classical novas, not dwarf novas or supernovae, identified by their chemical lines and the broad brightness curves shaping their light. In short, novas are both ordinary and extraordinary common events in the theatre of galactic evolution, yet each telling us something vital about how stars live, die, and sometimes flare back to life in one final outburst of cosmic glory. Part 7. The Anatomy of a Quake Cluster. Beneath Venezuela's Lake Maracaibo and the surrounding Zulia state lies one of South America's most geologically restless zones. Here, the Caribbean plate grinds relentlessly against the northern edge of the South American plate, producing a tangled network of faults that have been straining and storing energy for decades. Among the major actors in this tectonic drama are the Bocono Fault, which cuts northeast to southwest through the Andes, the Ocarancon system that threads east to west along the Caribbean coast, and the Santa Marta Fault that extends across the border into Colombia. In this compressed and fractured terrain, stress slowly builds until something slips, and the Earth releases it violently. That release came at 22:21 UTC on September 24th, when a magnitude 6.2 rupture tore open just 7.8 kilometers beneath the surface. At such a shallow depth, seismic waves had little time to disperse before slamming into population centers, amplifying the shaking across a wide swath of Venezuela and Colombia. The rupture likely extended kilometers along a fault plane with sudden displacement measured in meters, undoing years or decades of accumulated tectonic pressure in less than a minute. Seismic waves radiated outward at nearly 6 kilometers per second. Primary waves, P waves, arrived first in seismographs, compressing the ground in a back-and-forth shudder that most people barely noticed. Then came the S waves, shearing rock side to side, shaking buildings far more violently. Finally, surface waves rolled in more slowly but packed with destructive energy, creating the heaving wave-like motion witnesses described as lasting several minutes in some locations. But the Earth was far from finished. Barely 5.5 hours later, at 3:51 UTC on September 25th, another major rupture struck almost the exact same area. This one measured magnitude 6.3 and originated deeper, about 14 kilometers underground. Though slightly weaker at the surface than its shallow predecessor, it still produced intense shaking across the region. Most evidence suggests the second quake struck an adjacent fault segment, its timing likely triggered by stress redistribution from the first rupture. This domino effect, known as stress transfer, is why quakes often appear in clusters. When one fault slips, it relieves stress locally but reshapes the surrounding stress field, raising the odds of rupture nearby. In Venezuela's case, the September 24th quake appears to have redistributed strain directly onto the patch of crust that broke hours later. And while the difference between 6.2 and 6, the 3rd of May, sound trivial, on the logarithmic magnitude scale, it's massive. The second quake released almost twice the energy of the first. Combined, the two were equivalent to a single magnitude 6.4 to 6.5 event, significant enough to rank among the world's largest quakes in late September 2025. Not surprisingly, monitoring agencies across the globe reported slightly different magnitude estimates. Geological Survey based its values on moment magnitude, which calculates total energy release, while the European and Mediterranean networks relied on variations using surface or body waves. These methodological differences, later refined as fresh data flowed in, explain why headlines listed the first quake anywhere between magnitude 6.1 and 6.3, but regardless of the final tally, the human experience was the same: frightened residents rushing into the streets, buildings swaying, glass shattering, alarms blaring across Venezuela and into Colombia. Aftershocks arrived right on schedule. Later on September 25th, a magnitude 5.8 rattled the same region, though considerably smaller than the main shocks. It was still strong enough to damage weakened structures and fray nerves already stretched thin. This pattern follows Omori's law, an observation dating back over a century. After shocks decline in frequency and size as time passes, but they can continue for weeks, months, or even years. The largest often arrive in the days immediately following the main event, keeping entire populations on anxious edge. The geology of Lake Maracaibo explains why this zone is so treacherous. The basin is essentially a crustal graben, a down-dropped block defined by active faults. Over millions of years, these structures created the sedimentary layers that eventually trapped Venezuela's rich petroleum reserves. But they also left behind crust primed for fracture. Both September quakes struck in the upper crust, where rock is brittle and ruptures violently, compared to deeper zones where heat and pressure force rock to deform more plastically. Depth estimates carry uncertainty, but the values of 7.8 kilometers for the first quake and 14 kilometers for the second place them firmly in brittle crust, explaining their capacity to rock the surface so strongly. The timing, of course, raises questions. Could external forces like solar storms, atmospheric pressure, even lunar tides nudge faults into failure? Official consensus is firm. The United States Geological Survey and international seismological agencies see no reliable evidence linking earthquakes to space weather or solar activity. Decades of correlation studies consistently fail to establish predictive relationships between solar flares, CMEs, or geomagnetic disturbances and seismic events. That said, some researchers continue probing atmospheric pressure changes. Ocean tides and gravitational influences from the moon and sun do affect fault stress, but the shifts are minuscule compared to the forces required to trigger rupture. These subtle nudges might contribute only when a fault is literally balanced at the edge of failure. What ultimately drives events like Venezuela's twin shocks is stored tectonic stress, not signals arriving from the sun. Global monitoring organizations use detailed data like centroid moment tensor analyses to piece together the mechanics of these ruptures. By calculating fault geometry, slip direction, and the amount of energy redistributed, seismologists gain insights into how the September 24th and 25th events reshaped regional stress. That information matters not only for science but also for hazard assessment, building codes, and disaster preparedness in regions where millions live directly on shifting fault lines. For Venezuela, this quake cluster was more than just numbers on seismic charts. It was thousands of people evacuated from swaying towers, emergency teams rushing to hospitals and bridges, and citizens recording shaky videos on phones as the ground rolled beneath their feet. Once again, Earth reminded us that our planet is every bit as restless, dramatic, and unpredictable as the stars above. Part 8. The Sun at Maximum. While Venezuela's crust was reverberating with stress and aftershocks, another kind of energy release was building above our heads, this time across the surface of our own star. By 2024 and 2025, Solar Cycle 25 had roared to its climax, transforming the Sun into a restless powerhouse capable of hurling billion-ton storms of plasma across the solar system, and the final week of September found it at full intensity. On the very same days novas blazed in southern constellations and earthquakes shook the Venezuelan Andes, solar monitors lit up with indicators showing the Sun at peak agitation. A common index for measuring activity, the 10.7 centimeter radio flux, was hovering around 180 to 190 units. To the uninitiated, those numbers may seem abstract, but solar physicists know they paint a vivid picture. A reading above 150 signals elevated activity. Above 200 marks the kind of conditions where strong space weather becomes likely. By late September, our star was firmly in this danger zone. The visible signs were dramatic. Sunspots riddled the solar surface like crater-dark blemishes. Each one represents a tangle of magnetic fields rooted in the photosphere, often so large they could swallow Earth whole. Within some cores, Magnetic strength tipped past 3,000 Gauss, thousands of times the intensity of our planet's own field. And when those fields twist and reconnect, the results unleash solar flares, plasma eruptions and coronal mass ejections, CME cannon fire blasted directly into the heliosphere. But sunspot counts only scratch the surface. During solar maximum, the sun's field transforms from a relatively simple north-south dipole into something far messier, a twisted, knotted structure whose loops of magnetism number in the hundreds. Active regions, clusters of interconnected sunspots, spin across the solar disk, persisting for weeks and occasionally detonating in eruptions visible across the solar system. When a CME occurs, the scale is staggering. Its magnetic energy from the corona suddenly releases, flinging immense clouds of charged gas into space. These explosions weigh billions of tons and accelerate at speeds from a slow 250 kilometers per second to a blistering 3,000. At maximum speed, that plasma reaches Earth's orbit in just over a day, compressing the solar wind ahead of it into shock waves and energizing particles to near-relativistic speeds. NASA's NOAA Space Weather Prediction Center follows each storm using the WSA INDLIL model, a massive computer grid that simulates the solar wind as it moves outward in 3 dimensions. It maps density, speed, and direction, and works out the orientation of the interplanetary magnetic field, a key to predicting whether Earth might get struck head-on. The simulations can't capture every twist and filament of magnetic structure, but they provide accurate windows of when and where CMEs are likely to collide with planets, satellites, or any object caught in their path. The Earth itself is particularly vulnerable during the equinoxes. Around March and September, the orientation of the planet's magnetic dipole aligns in such a way that it couples more easily to the solar wind. This Russell-McFerrin effect means even moderate storms can trigger geomagnetic chaos. Auroras shimmer further south than usual, power grids run hot with unwanted currents, and communication systems warp under disturbed ionospheric conditions. And while the northern lights capture global awe, the hidden impacts reach deeper. Aviation routes at high latitudes lose stable radio connections. Satellites experience atmospheric drag as Earth's outer atmosphere swells. Electrical power infrastructure risks overload. For these reasons, NOAA tracks impacts across 3 scales: the G scale for geomagnetic storms, the R scale for radio blackouts, and the S scale for solar radiation events. Operators across aviation, spaceflight, and power industries rely on these warnings the way coastal communities rely on hurricane forecasts. Comets, meanwhile, become laboratories for studying those same phenomena in action. When a comet approaches the inner solar system, it grows a dust tail pushed gently by sunlight, and an ion tail stretched straight by the solar wind's embedded magnetic field. If a CME runs into that tail, the result can be violent. In 2007, European spacecraft caught just such an event, a coronal mass ejection slamming into Comet Encke, severing its entire ion tail, which drifted away like a cosmic smoke plume before a new one started forming. That precedent suddenly mattered again in 2025. The 3I Atlas, the interstellar visitor, entered the most dangerous theater possible, the ecliptic plane, exactly where much of the solar system's magnetic fury plays out. Unlike Oumuamua, which zipped through too quickly, or Borisov, which stayed comparatively distant, Atlas was forced to endure the sun's tantrums head-on during peak cycle. The active backdrop of solar cycle 25 ensured that it wasn't just one CME drifting past. It was many, colliding, merging, accelerating, layering complexity upon complexity. Plasma clouds crashed into each other, forming compression regions, magnetic shears, and particle accelerators that turned empty space into a kind of storm-tossed ocean. For forecasters and scientists, it was a living physics lab far beyond what we could recreate on Earth. Every eye was on the sun. NASA's Solar Dynamics Observatory streamed ultraviolet portraits of the corona boiling with loops and jets. SOHO monitored eruptions from the far side. AC, sitting in the LEL 1 point between Earth and Sun, gave us an upstream taste of the solar wind before it reached home. Amateur radio networks worldwide filled out the picture with real-time reports of how signals warped and bent under geomagnetic interference. Together, these threads stitched a story of a sun at its most unpredictable, violent, magnetic, and restless. And by all signs, solar cycle 25 wasn't delivering a single dramatic peak, but a double crest, keeping activity high into late 2025. For scientists, this created a perfect storm: an active sun, equinox coupling, comets losing their tails, novas shining from afar, and human instruments sophisticated enough to watch all of it simultaneously. Part 9. 3 Itelis on approach. As auroras painted the skies and social media buzzed with viral images of red, green, and violet atmospheric displays, space forecasters were tracking something even more extraordinary: an alien visitor threading its way through the very heart of the solar system. For the first time, an interstellar object was about to encounter our neighborhood during the peak of solar maximum. In the early hours of July 1st, 2025, the Atlas telescope survey flagged a faint, slow-moving object against the starfield. At first it resembled a comet, just another icy speck casting off gas. But orbital calculations changed the story completely. Anamashri, the Ebal Solarmillion. The path was not elliptical like every native comet, but hyperbolic, a trajectory with an eccentricity greater than 1, ensuring it would never stay bound to the sun. This was not a local comet. It was a traveler from the stars. Its official designation, 3I Atlas, tells the whole story. The third interstellar object ever confirmed, discovered by the Asteroid Terrestrial Impact Last Alert System. Following Oumuamua in 2017 and Comet Borisov in 2019, Atlas had joined one of astronomy's most exclusive clubs. Unlike its predecessors, though, this visitor arrived under a perfect alignment of circumstances. Oumuamua zipped through in weeks too fast and faint for detailed study. Borisov stayed at a safer distance, difficult for telescopes to resolve. But Atlas is different. Its orbit lies close to the ecliptic plane, the crowded disk where planets, comets, and most solar activity unfold, and it entered the inner system right as solar cycle 25 was exploding into its maximum. That timing gives scientists an unprecedented laboratory, a chance to watch how the sun's most violent weather interacts with frozen material formed around an entirely different star. Atlas is a retrograde traveler, tilted at about 175 degrees to the planetary traffic lanes, essentially moving backward relative to every major world's orbit. Estimates of its size remain rough, anywhere between a few hundred meters across to as large as 15 kilometers in diameter. Even the world's biggest telescopes see it only as a shimmering point with a hazy coma. Whether its surface is reflective, dark, icy, or dust-laden makes calculations tricky. But one thing is certain: this object carries chemistry forged in another stellar system, billions of years and trillions of kilometers removed from our own. October 3rd, 2025 is the milestone circled on every astronomer's calendar. That's when Atlas will swing past Mars, at just 0.19 astronomical units, around 28 to 30 million kilometers, cosmic speaking distance. Mars orbiters will be in perfect position to grab a front-row look. NASA's Mars Reconnaissance Orbiter, with its high-rise camera capable of pinpointing details as small as a dinner table on Mars itself, will turn its lens toward Atlas. From that distance, the camera will resolve features on the scale of about 30 kilometers, not enough to map a nucleus, but possibly enough to distinguish a dense core from a diffuse, dusty coma. The science payoff, however, extends beyond photography. Spectrographs aboard orbiters like ESA's ExoMars Trace Gas Orbiter will attempt to reveal Atlas's chemical fingerprint. As sunlight bakes the nucleus, gases locked away for eons will escape into space. Astronomers are anticipating sharp spectral lines for cyanogen, carbon monoxide, and carbon dioxide, all signposts of the molecular ingredients that condensed around a distant star light-years away. For the first time, we may directly sniff the chemistry of another solar system. Amateur astronomers have joined the chase as well. The comet's brightening has been faster than expected, suggesting either its size or its activity is greater than models predicted. Its southern position favors observers below the equator, but northern hemisphere watchers can still track it low on their southern horizons before dawn. The collective effort backyard telescopes syncing with professional observatories has created a global watch party unlike any before. Every photometric point, every spectrum, every image helps refine models of how this foreign object behaves as it dives closer to the Sun. Its next act arrives on October 29th, when Atlas reaches perihelion, its closest sweep to the Sun, hovering around 1.36 to 1.4 AU. That's farther than Earth's orbit, but close enough for ground and space-based observatories to keep watch. How it responds to direct solar heating is the big question. Will it behave like a normal comet, shedding dust and brightening gradually, or will it show us signatures never before seen, betraying its alien origin? Then December 19th brings Earth's best chance. Atlas will pass within 1.8 AU, about 270 million kilometers. That's significantly closer than Mars is at its farthest point, affording astronomers months of observing opportunities. Both powerhouse observatories and backyard telescopes will contribute to a communal period of monitoring, tracking tail structures, jets, and sudden brightening events. The visitor's behavior could offer profound insights. Hydrogen, carbon-bearing molecules, and even dust patterns may reveal how comets form in entirely different stellar nurseries. Volatiles frozen during its eons in interstellar space could erupt spectacularly, releasing ancient secrets of environments we will never directly see. Early observations have already stirred intrigue. Professionals report classic antisolar ion tails, but some amateur accounts suggest unusual dust geometries, seemingly breaking the rules of comet physics. The explanation likely lies in the difference between dust and gas tails, dust grains bending with radiation pressure and orbital geometry, while ion tails remain magnetically tethered to solar wind lines. The contrast is a reminder. Interstellar visitors may look superficially like solar system comets, but the subtleties can reveal something wholly exotic. For now, even its size remains unresolved, as brightness depends on surface reflectivity, activity, and dust liberation, all still unknown. Thermal modeling paired with infrared data will eventually refine those numbers. Until then, 3i Atlas remains a fuzzy ball of alien ice, dust, and gas, carrying the fingerprints of a star that is not our Sun. And by sheer coincidence, or cosmic choreography, it arrived just as Earth was rocked by quakes, novas flared in southern skies, and our own star erupted in storms. This is only the beginning of what Atlas might show us. For months to come, we'll be peeling back the layers of what an interstellar object looks like when it meets our stormy star at maximum. As if the arrival of 3 Atlas weren't enough to electrify October's skies, the interstellar visitor will share the stage with another dazzling performer, a newly discovered comet that could make this month one of the most memorable in skywatching history. Comet CEA's 2025 R2, now nicknamed Comet Swan, was first spotted in early September by amateur astronomer Vladimir Bezugi, pouring through data from Al-Soho, the Solar and Heliospheric Observatory. SOHO's Swan instrument normally maps hydrogen emissions flowing through the solar system, but occasionally its images reveal something unexpected. While scanning, Bezugi noticed a brightening patch that didn't match any logged star, comet, or asteroid. Careful analysis across multiple frames confirmed the truth. A brand new comet, never before seen, swinging into the inner solar system on its maiden recorded voyage. The discovery came right as the comet was making its closest approach to the Sun, or perihelion, on September 12, 2025. This sudden sunlight exposure explained the flare of brightness that set alarm bells ringing. Comets tend to bloom dramatically as they near perihelion, with heat-freeing volatile ices into clouds of gas and dust, creating the glowing comas and sweeping tails that capture imaginations on Earth. What makes Comet Swan exceptional is not just its timing, but its trajectory. In late October, it will skim close enough to Earth to potentially reach naked-eye brightness, with predictions ranging from magnitude 4 to 6. For anyone watching under dark skies, that's faintly visible without equipment, though binoculars or a backyard telescope will reveal far richer detail, its luminous atmosphere, evolving tail, and subtle shifts in structure. The southern hemisphere initially enjoys the best vantage point, but as the month progresses, northern hemisphere observers will gain excellent views around the comet's peak. Then comes the kicker. Comet Swan's closest Earth approach aligns almost perfectly with a new moon on October 20th, 21st, sparing observers the glare that often drowns out faint objects. On those same nights, the annual Orionids meteor shower hits its peak, sending Halley's comet debris streaking across the sky. For skywatchers, it doesn't get much better. A naked-eye comet, glittering meteors, and the interstellar mystery of Atlas still unfolding as it passes Mars, all converging within the same span of dark autumn nights. The contrast between Swan and Atlas makes the narrative even more compelling. Atlas is the alien outsider, carrying molecules frozen around a star we'll likely never see. Swan, meanwhile, is native, a long-period visitor likely freed from the Haunter cloud, the icy backwaters of our solar system where countless pristine comets linger. While Atlas offers clues about the chemistry of other star systems, Swan shows us our own history, what the young solar system was made of 4 billion years ago, and how those primordial materials react when nudged out of cold storage and ignited by solar heat. Scientists and amateurs alike are already preparing to seize the dual opportunity. Astronomy forums buzz with plans for side-by-side imaging campaigns, where wide-field cameras can capture both Atlas and Swan in the same frame. Time-lapse photography will reveal shifting tails, swelling comas, and the daily unpredictability of cometary evolution. As October nights pass, differences between ion tails, dust trails, and outgassing patterns will provide invaluable clues to both interstellar and solar system chemistry. But with comets, nothing is guaranteed. Some exceed their forecasts spectacularly, erupting into brightness that dominates the sky, with classical tails stretching across constellations. Others fizzle, fading before they peak or catastrophically fragmenting into smaller pieces. As a newly discovered long-period comet, Swan has no track record, no historical apparitions to guide predictions. Its behavior could exceed our wildest hopes or collapse into disappointment. That uncertainty is precisely what makes following a comet so thrilling. And so October 2025 shapes up as a rare and perhaps unrepeatable convergence, an interstellar wanderer brushing by Mars, a newborn comet glowing in Earth's skies, and a meteor shower punctuating the performance. With the sun itself in a cycle of wild storms, the heavens seem determined to remind us, all at once, of their restless beauty. Part 11. Cosmic Coincidences or Patterns. October 2025 feels like a month. The universe scripted with deliberate flair. To see how extraordinary this timeline looks when all events are placed together, let's lay them out. On September 23rd, a nova in Centaurus, V1935, suddenly blazed to naked-eye visibility. Just one day later, on September 24th, Venezuela endured a magnitude 6.2 earthquake. Hours after midnight on the 25th, a second nova erupted in Sagittarius, V7994, while yet another rupture tore through the same Venezuelan region, this one a magnitude 6.3, paired with a powerful 5.8 aftershock. During those very same days, solar weather forecasts, using the Endel computer model, showed coronal mass ejections threading the projected path of the recently discovered interstellar visitor, 3I Atlas. Then came October. On the third Atlas swept just 0.19 AU past Mars, a front-row pass for orbiting spacecraft. Barely 2 weeks later, on October 20th and 21st, Comet Swan reached its closest approach to Earth, its timing perfectly overlapping a new moon and the peak nights of the Orionid meteor shower. Finally, on October 29th, Atlas reached perihelion, its tightest approach to the Sun, exactly when solar activity remained at maximum storm levels. Pack it all together: twin novas, twin quakes, magnetic storms, a wandering interstellar comet passing Mars, another long-period comet swinging close to Earth, all in just over a month. At first glance, it doesn't feel like coincidence. It looks choreographed, like the cosmos had cued a script of crescendos and climaxes. And yet, science tugs the reins. Patterns emerge because human brains are designed to find them. For survival, our ancestors had to be attuned to subtle associations. The rustle in tall grass might signal danger, or a certain cloud meant storms. This ability, pattern detection, remains hardwired into us. So when multiple rare events cluster together, our instincts lean towards significance, even if each event is causally unrelated. Psychologists call this tendency apophenia, the impulse to see meaning in coincidental noise. It's both a strength and a weakness of cognition. Without it, humanity might never have discerned seasons or recognized recurring cycles that let us build art, science, and agriculture. But it also makes us eager to stitch together links where none exist. The mainstream scientific interpretation of late September and October 2025 is straightforward. The US Geological Survey states unequivocally, no mechanism connects earthquakes to solar storms or space weather. Decades of statistical analyses confirm that geomagnetic activity does not predict seismic events. Seismologists agree that prediction remains impossible, whether using tectonic stress models or speculative space weather influences. For novas, likewise, the physics is accounted for. Astronomers understand them as natural flashpoints in binary star systems, when white dwarfs gorge on stolen hydrogen until runaway thermonuclear fusion ignites. Timing can't be tied to earthly quakes or solar activity. It follows the rules of stellar evolution, not human perception. The novas of 2025, despite their perfect alignment with ground tremors and solar chaos, fall neatly within expectations of stellar physics. And CMEs, again well studied. They are simply the natural result of the sun's knotted magnetic fields during solar maximum, a phase known to bring clusters of eruptions. Their timing, while dramatic, fits solar statistics. So if science assures us these aren't connected, why does it still feel like something greater is unfolding? Why does the clustering stir a deeper wonder, a suspicion that maybe, just maybe, there's more to be seen than randomness? Perhaps the answer lies in the paradox of perspective. Science gives us clarity to see each mechanism working independently, while our human pattern-seeking minds invite us to hold space for mystery. Both are valuable. You can honor the rigor of seismology, astrophysics, and plasma physics, while still stepping back to marvel at how the cosmos sometimes seems to arrange events into a tapestry of apparent synchronicity. Because even if coincidence explains it all, the timing remains undeniably remarkable. In one single month, humanity witnessed the Earth groan, stars ignite into sudden outbursts, the sun unleash storms of magnetized fire, and alien matter drift through our neighborhood. That alone is worth all, without needing mysterious links behind it. What we do next is what matters. Document what instruments confirm, study what physics explains, but also allow ourselves the wonder of watching reality edge so close to myth. Part 12. Space Weather and Earthquakes. Few ideas stir more controversy in Earth and space science than the suggestion that storms on the sun could somehow influence quakes deep in Earth's crust. The hypothesis has been debated for decades, alluring because it hints at hidden links between our star's tempests and the tremors beneath our feet. But every time researchers look closely, the data resists simple answers. Scientists have long documented the basics. Coronal mass ejections, solar flares, and high-speed solar wind streams pound Earth's magnetosphere. Those space weather events generate auroras, disrupt radio, and affect satellites. Some researchers claim they may also line up with clusters of seismic activity on Earth. Patterns appear in charts and catalogues, but what's missing is a convincing physical connection. How could electromagnetic fluctuations 150 million kilometers away unleash a rupture in the solid rock of the crust? One of the more recent models comes from Stephan Burns, who tried to sketch out a possible chain of influence. He proposed that sudden drops in solar wind density, moments when dense, high-speed plasma streams give way to sparse background wind, might create subtle changes in Earth's electromagnetic environment. Imagine the solar wind as pressure against the magnetosphere. When that pressure collapses, the shield surrounding our planet would shift in size and configuration. Those changes, in turn, might rewire the currents flowing through Earth's ionosphere, currents strong enough to induce tiny electromagnetic fields inside crustal rocks. Some minerals, being piezoelectric, respond by generating microstresses. Technically, the physics all exists, but the scale is the problem. The fluctuations proposed are measured in nanotoslars of magnetic field strength and microstrain levels inside rock, magnitudes thousands of times too weak to budge a fault unless it was already balanced on the knife's edge of rupture. The plausible coupling steps are there, but stacked together, each adds attenuation, leaving most geophysicists unconvinced these influences matter on any meaningful scale. What has been established is less about proof and more about persistence. Dozens of statistical studies continue to appear, suggesting links between geomagnetic activity and seismic clustering. Some claim flares correlate with earthquake timing. Others plot CME impacts against tremor catalogs, reporting upticks around strong storms. But when independent teams try to replicate those findings across different regions, time spans, or seismic datasets, the results often vanish. What looks convincing in one window collapses when tested against another. Publication bias clouds the waters further. Positive findings, evidence that solar events sync with quakes, are far more likely to be written up, published, and cited. Null results fade into obscurity, leaving the impression of stronger links than reality supports. The true record is messy, a handful of intriguing alignments wrapped in a mountain of statistical noise. Seismologists remain clear. No demonstrated causal mechanism ties solar storms to earthquakes. At most, if such effects exist, they are faint, indirect, and only capable of triggering quakes already at the breaking point. The energy locked in tectonic faults dwarfs the tiny nudges that space weather could provide. Earthquakes are powered by stresses building for years or centuries, waiting for a fracture threshold, not by fluctuations in the upper atmosphere. Still, the persistence of this idea reveals something beyond physics. Humans want the cosmos to connect. We are drawn to the narrative in which solar storms breathe on Earth and trigger hidden fault lines, making quakes feel like part of a grand choreography rather than isolated mechanical failures. Even with rigorous science chipping away at the idea, speculation persists, alive in the space between evidence and imagination. In a sense, the debate itself mirrors the broader theme of late 2025, science reminding us of boundaries while human instinct itches to stitch disparate wonders into one tapestry. Flares, novas, comets, quakes, they unfold independently. But given how they clustered across weeks, minds reach for pattern, and even when science denies a true connection, the allure of cosmic resonance lingers. Part 13, Novae and Climate. The notion that stellar outbursts could somehow shape Earth's climate stretches across scales so vast they're difficult to comprehend. Compared to the earlier idea that solar storms might nudge fault lines, this question leaps outward into deep time and cosmic distance. Could the explosions of distant stars influence our atmosphere, or even our planet's fate? At first, the numbers sound persuasive. A typical nova unleashes as much energy as our sun would radiate across 10,000 years, on the order of 10, 43, 10 and dome, 43. Bialzier. It's a figure so large we struggle to wrap our minds around it. To put it in human terms, that single blast carries more power than our entire civilization would consume in billions of years at current rates. But here's the crucial catch: distance. That energy doesn't beam straight at us like a laser. It spreads evenly, spherically, diluting as it races outward through the interstellar dark. By the time the light from nova V 1935 Centauri, or its companion V 7994 Sagittari, finally reached us in September 2025, it had thinned to the level of ordinary starlight. Yes, they burst into naked-eye brilliance in our night skies, but the additional radiation reaching Earth amounted to little more than a few extra photons per square meter, less energy than a flashlight aimed at you from across a football field. This makes the climate impact effectively zero. Even if you combined both September novae, the total energy arriving at Earth during their weeks of visibility would not heat a single cup of coffee by a detectable amount. That's the scale difference between what happens out there and what trickles down here. They are spectacular to observe, but they are aesthetically powerful, not environmentally disruptive. Supernovae are a different story. Unlike novae, supernovae truly reset the table of the cosmos. Now these final detonations can outshine entire galaxies and hurl gamma rays, X-rays, and cosmic particles across space. Astronomers estimate that if one went off within 50 light-years of Earth, the consequences could be dire: substantial destruction of ozone, dangerous levels of UV radiation reaching the surface, long-term atmospheric disruptions, and possibly mass extinction. Our fossil and geological records hint that such events may have brushed Earth in deep time, but novae like Via, Mava, or 1935 Centauri and V 7994 Sagittari Don't fall into that league. They're distant fireworks from binary systems, pieces of theatre written thousands of years ago, but only now arriving in our skies. Their effect is wonder rather than threat, symbolism rather than hazard. From a climate lens, they are negligible. From a human lens, their timing amid solar storms, comets, and earthquakes gives them meaning, whether or not the physics connects the dots. So while September 2025's novae captured headlines, the truth is stark: they cannot stir our atmosphere, alter Earth's chemistry, or disrupt climate cycles. To borrow a metaphor, they are postcards from across the galaxy, sent centuries before we knew how to read them. They illuminate our sky, not our weather. That said, the question itself opens doors, because while novae lack the raw intensity to affect us directly, their bigger siblings, supernovae, hypernovae, gamma-ray bursts, do represent credible astrophysical threats on geological timeframes. And the fragile shell of our atmosphere, which shields us from lethal ultraviolet, is a reminder of just how interwoven Earth and the cosmos truly are. The September 2025 novae will fade, their light dimming back into the tapestry of stars, but the questions they prompt about vulnerability, significance, and cosmic influence, they remind us how easily human imagination stretches from awe into speculation, from spectacle in the night sky to thoughts of planetary destiny. Part 14. Interstellar Visitors as Solar Probes. For most people, 3i Atlas is a curiosity, a chunk of ice and rock wandering from another star. But to scientists, it represents something much more profound. It may be the single best natural probe we've ever had for testing how our sun's magnetic fury shapes and transforms material not born in our solar nursery. If ordinary comets are like weather balloons drifting through space, 3i Atlas is an alien instrument, carrying chemical truths from another stellar system into the storm of solar cycle 25. Other interstellar objects gave us only brief glimpses. The Oumuamua zipped by too quickly for telescopes to do more than speculate. Borisov moved through at a safer distance. Interesting but limited for close investigation. Atlas, however, has wandered into the heart of the action. The ecliptic plane itself, the sheet of space where solar wind is thickest, magnetic fields are most tangled, and planets resourcefully orbit. It has arrived not during quiet times but in the middle of solar maximum, exactly when coronal mass ejections explode most often and magnetic chaos peaks. Think of comets as living measuring sticks for invisible forces. Their Orion tails, stretching away from their nuclei, are literal traces of the solar wind's magnetic threads. When those tails bend, snap, or brighten, they reveal plasma conditions that satellites can only sample point by point. Astronomers have long used our system's comets as remote detectors of solar wind speed and field orientation. Atlas offers the same opportunity, but with materials forged around another star billions of years ago. If the sun rips off its iron tail or reshapes its coma, we'll be watching the first documented interaction between our star's storm and alien chemistry. The timing of its Mars flyby could hardly be more fortunate. On October 3rd, Atlas will swing within 0.19 AU of the red planet, about 28 million kilometers. Spacecraft orbiting Mars like the European Space Agency's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter will be in position to observe. From that distance, the high-rise camera aboard MRO should resolve scales of about 30 kilometers, far too coarse to map the nucleus directly, but enough to separate a dense core from an extended coma. More importantly, with telescopes on Earth and spacecraft around Mars watching simultaneously, the parallax effect gives astronomers a rare way to pin down Atlas's size and activity level far more precisely than one vantage point alone could deliver. Instrumentation designed for Martian atmosphere studies may accidentally become interstellar experiment kits. ExoMars's spectrometers, built to sniff Martian trace gases, could be repurposed to capture signatures escaping from Atlas itself. Molecules like cyanogen, carbon monoxide, or carbon dioxide, all frozen for untold millennia, might show up as sunlight warms the object, revealing chemical details about conditions in the distant star system where it was born, a kind of forensic fingerprint across light. Back on Earth, the campaign is massive. Professional observatories and amateur networks alike are coordinating through the Minor Planet Center, timing exposures, comparing spectra and logging brightness curves. The global coverage ensures that every piece of Atlas's evolving behavior is documented: the swelling coma, the flicker of jets, the angle of its tail, and the changes wrought by solar storms. In essence, Atlas has become a free, alien-built instrument for heliophysics, drifting straight through the core of solar activity at the exact peak of a cycle that surges only once every 11 years. It is rare, almost uncanny, that the universe would send a probe from another star during our technological era, at a moment when we are fully capable of measuring it from Earth, from orbit, and from another planet entirely. That is why scientists are calling Atlas unprecedented. It's not just another comet, it's a messenger carrying the chemistry of a foreign world, now answering to the breath of our sun. Part 15, Looking Forward, October and Beyond. Circle the dates: October 3rd, October 21st, October 29th, then underline December 19th in bold. These aren't just calendar markers, they're moments when the universe will press pause on ordinary life and unveil something extraordinary. Each date represents a milestone in our unfolding ability to observe interstellar visitors, watch space weather shape alien matter, and compare comets of vastly different origins, all under the theatre of an active sun. The first act comes October 3rd, when 3i Atlas swings within 0.19 astronomical units of Mars, about 28 million kilometers from the red planet. In all of human history, we've never had an interstellar object pass so close to a world where orbiters with precision instruments were already waiting. NASA's Mars Reconnaissance Orbiter and ESA's ExoMars Trace Gas Orbiter have shifted schedules to capture every possible observation of this encounter, a cosmic blind date between alien material and our robotic eyes on Mars. The geometry from Mars's vantage point creates opportunities Earth cannot match. From Mars orbit, we'll see Atlas from different angles, potentially solving puzzles about its size, shape, and activity that one viewpoint alone could never pin down. Simultaneous Earth and Mars data offers parallax, the triangulation of measurements that transforms a distant blur into clearer physical numbers. The excitement comes with a caveat, however. Atlas will still appear as a star-like speck for most instruments. Even HiRISE, with its famously sharp eye, will only achieve about 30 kilometers per pixel, far too coarse to capture surface details. But that's not the disappointment it may sound like. What's possible here is even more valuable: refined constraints on activity, gas composition, coma structure, and brightness evolution, all forced into sharper focus by the tag team observations of two planets. The real payoff lies in chemistry, light curves, and tail morphology, not in glossy resolved images. Then, October 20th and 21st, a second performer takes the stage. The comet Cees 2025 AL2, better known as Comet Swan, makes its closest sweep past Earth at about 0.26 AU. Its timing could not be better. The new moon clears away light pollution from the sky. At the same time, the Orionid meteor shower peaks, sprinkling debris from Halley's Comet overhead. If Swan brightens as predicted to magnitude 4 or even 6, casual stargazers may glimpse it without instruments, while binoculars or small telescopes reveal its coma and tail. But comets are tricksters. Some flare into brilliance, far outshining forecasts. Others sputter, fragment, or dim into anticlimax. Their unpredictability is part of their allure. And while Swan is technically a native comet carrying the icy recipes of our early solar system, it will be framed on those nights alongside Atlas, the interstellar outsider, carrying chemistry from another star. For possibly the first time in history, observers may compare a solar system comet and an interstellar visitor under the same dark skies. October 29th marks Atlas's perihelion, its closest pass to the Sun at around 1.36 AU, just beyond Earth's orbit. As solar heating intensifies, astronomers expect volatile compounds to boil from its surface, testing its resilience and changing its coma, possibly with dramatic bursts of activity. This will be a make-or-break moment. Does Atlas behave like an ordinary comet, or does it unveil something truly alien in its response to the Sun's full fury? Finally, December 19th offers Earth's closest encounter, 1.8 AU, about 270 million kilometers. At that distance, Atlas will still appear faint, but close enough for continuous study by Earth's largest telescopes, amateur astronomers, and perhaps radio and space-based observatories. The prolonged window allows weeks of monitoring from late October into the start of 2026, ensuring we don't just catch highlights but follow its entire journey through the inner solar system. These converging dates create perhaps the richest observing season in living memory. One interstellar object, one long-period comet, a peak meteor shower, solar storms raging at maximum, and the instruments of two worlds, Earth and Mars, trained on the spectacle. October 2025 won't just deliver a viewing opportunity. It promises insights into chemistry beyond our solar system, the physics of space weather, and the earliest building blocks of stars and planets. The next few months won't only test our telescopes, they'll test our imagination, because whether or not patterns truly connect, the compression of these cosmic events into one brief chapter of human history leaves us asking the age-old question, accident or design? October 29th will deliver the moment many astronomers have waited for, the exact perihelion of 3 Alnisapis. At 1.36 AU, just outside Earth's orbit, it will endure the harshest solar heating of its journey. This is where the fate of its icy nucleus will be decided. Compounds locked away for millions of years, frozen since the birth of another star system, could suddenly boil out, creating dramatic tail development, bursts of brightness, or even partial breakups that distinguish this alien traveler from our familiar solar system comets. Perihelion is also when Atlas may reveal its true personality. Will it mimic the predictable behavior of typical comets, or will it remind us of its interstellar strangeness? Across the globe, professional observatories have put the date into priority schedules. Coordinated campaigns will monitor its increase or decrease in brightness, track the coma's expansion, watch tails shift under solar winds, and capture spectra that indicate its chemistry. Amateurs, too, armed with CCDs, digital cameras, or even binoculars, will provide the continuous coverage professionals can't. Together, these collective eyes will follow the visitor during the exact moment it confronts the sun's peak fury. Then December 19th supplies Earth's best vantage point. At about 1.8 AU, closer than Mars when it wanders farthest from our planet, Atlas will still be faint, but well within reach of large telescopes, small observatories, and even dedicated hobbyists. Unlike the fleeting flyby of Oumuamua or the distant arc of Borisov, Atlas is granting humanity the gift of time, months at least, with opportunities stretching into early 2026, to watch how an interstellar body changes under the constant push and pulse of solar weather. But expectation must be paired with reality. Despite dramatic headlines, naked eye brilliance is unlikely. Most changes will be subtle, gradual rises in brightness, shifts in composition visible only in spectroscopy, and evolving morphology that appears clearly only in long exposure imaging. Media may clamour for jaw-dropping visuals, but the true breakthroughs will come from careful analysis, chemical fingerprints, isotopic ratios, and data across wavelengths invisible to human eyes. If Atlas is extraordinary, the evidence will be numbers, spectra, and physics, not spectacular fireworks. Meanwhile, the rest of the stage remains just as dynamic. Solar Cycle 25 continues its maximum, bombarding Earth's magnetic bubble with coronal mass ejections. The Russell-McFerrin effect, active during the equinox, amplifies geomagnetic impacts and heightens auroral activity. Expect green curtains and red ribbons of northern lights to spill further south than normal, thrilling night sky photographers and confounding GPS and radio operators. NOAA's Space Weather Prediction Center and ESA's observatories track it all in real time, issuing G-scale storm alerts, R-scale radio blackout warnings, and S-scale solar radiation warnings for aviation and satellites. The sun is no gentle backdrop, it is an active character in this larger cosmic play. On Earth's own stage, Venezuelan aftershocks continue, as expected for quakes of 6.2 and 6.3 magnitude. Seismological teams track stress redistribution along the complex web of South American and Caribbean faults. Scientists remind us that tectonics, not solar storms, drive such quakes, and yet, as our minds replay the September clustering of novae quakes and space weather, we can't help but frame these events together. The novae, too, fade but persist in observation. V1935 Centauri and V7994 Sagittari continue their slow decline into anonymity, their light curves and spectra still teaching astronomers about dust formation, hydrogen shell expansion, and shockwave particle acceleration. Amateur observers and professional telescopes alike remain engaged, logging data across months to years, because novae are not single-night fireworks but evolving laboratories of stellar physics. Some may dim spectacularly as dust dips shroud them, then re-brighten as clouds scatter and clear, gifting us second acts. All these events, Atlas under solar fire, Comet Swan, solar maximum storming overhead, two southern sky novas burning out, Venezuelan quakes fracturing crust, stand separately within rigorous science. Each obeys its own natural laws, yet taken together, they feel like narrative. They create the impression of rhythm, of a script written across domains as different as stellar evolution, seismic mechanics, orbital dynamics, and solar magnetism. Coincidence? Most likely, but meaningful in effect. Absolutely. The challenge, as always, is balance. To hold skepticism and wonder at once. To separate media hype from careful measurement. To treasure the fact that, in our time, we possess the tools to track all these scales simultaneously. Telescopes tuned to gamma rays, networks of seismometers, satellites mapping solar wind, backyard stargazers wielding digital cameras. No civilization in history had this breadth of vision, this simultaneity of awareness. Past generations saw comets flare, or felt earthquakes strike, but they never knew the full cosmic cast acting on the same stage. What October 2025 and beyond are giving us is not just discovery but perspective. A reminder that we live in a dynamic universe where stars explode, planets tremble, suns rage, and visitors drift in from infinity. They remind us that science and wonder aren't opposites but partners. We measure because we're curious, and we marvel because what we measure often dwarfs what we expect.